we pulled off some points, and then for number 2, we wrote an equation of that. So for number 2, you guys should have the equation we came up yesterday was that y equals 0.5x plus 1.6. Okay? So we came up with that yesterday. We sat there together. We went through the process of writing the equation of the line through 2 points. Okay? So this part of the graph was like where he was walking away from the CBR, and so as time was ticking this way, the distance was getting further and further away. Okay? The second portion of the graph, we pulled off 2 points, and then we wanted to write an equation there as well. We did that one while we were writing down the points because it just ended up being a horizontal. So at this part of the graph, he had walked away from the CBR and then stood there for a while. Okay? And so when we pulled points off of here, we saw the y coordinates were the same, and we remembered that for a horizontal line, the equation would just be y equals whatever y coordinate those points had, which in our situation was 2.7. Then, in number 5, you had the points, and it was your job in class during those last 5 to 8 minutes or at home, finished, writing the equation of the line that passed through these 2 points. So for number 5, the points that we pulled off were 4.2, 2.4, and 4.7, 2.1. So let's look at this and check if we did this correctly. Okay? So remember what we talked about in order to get our equation in slope-intercept form. The first thing we needed to find was a slope to plug into our equation. And the way that we would do that with our points is we would take one y coordinate, subtract the other, and then one x coordinate and subtract the other. So I'll do 2.1 minus 2.4 over 4.7 minus 4.2. So I'll get negative 0.3 over 0.5. Okay? When you guys divided that out, what did that give you, if anybody knows? 0.6? Negative, right? Okay, because at this point in the graph, remember, so he had walked away from the CBR, he had paused, and then he started walking back towards the CBR. So as time was going, the distance was getting closer, and that line that it's creating has a negative slope. So it makes sense that our calculation came out to be negative. So at this point, we know y is going to equal negative 0.6x plus some y-intercept. How did we say we could go about determining what our y-intercept is? Yes. Good. Plug in one of the points. I don't know. Do you guys have any preference? No? All right. I'll just do the first one. So remember, this is my x and this is my y. So 2.4 gets to be plugged in for y as long as I plug in 4.2 for x at the same time that is happening. And then I just have this small equation to solve for b. So I need to multiply 0.6 times 4.2 So I get negative 2.52 plus b. If I do some arithmetic wrong, tell me. And then I'm going to add 2.52 to both sides of the equation and determine that b is equal to 4.92. Okay? So my final equation for this portion should be that y is equal to negative 0.6x plus 4.92. How many of you guys were successful in figuring out that third equation? Okay, good job. All right, those of us that weren't, that's fine. We just got to practice and make sure that we know how to write the equation of a line given 2 points. So I'm going to record that over here also. And then I need one more piece of information from you guys. I took a picture of our data yesterday because it changed for third period. But my picture cut off what our ending mark was for the first section. So it ended at what? 2.6? Okay, thank you. All right. So what we want to do is we want to determine how you actually write the equation for this, okay? But in doing this, we're trying to review some of the skills that you guys already have. So the first skill we want to review is how do we just graph things on the graphing calculator? And if we go and graph the 3 lines that we got, is the picture going to look like the picture that we saw when our volunteer walked and made the graph on the CBR? Okay? So if you have a graphing calculator, take it out. If you don't have one, you're welcome to use one of mine. Make sure to put your ID in and watch out for the ones that have notes that like certain buttons don't work. If we don't have enough for anybody, everybody will buddy up and share. Okay? Brief reminder about how to do things on the graphing calculator. So all the graphing keys are the buttons that are up at the top. Some of you are really good at this from last year. Some of you are like, I never touched one and I didn't want to. We're going to be using them at different times in our class to help us with little things. We're going to be using them later this week or next week for an investigation. So as long as we can get the basics, we'll be good. So to type in an equation, you're going to go up here to the y equals button. And we basically want to clear out anything that's already written there so we can type in our 3 equations. So first of all, see across the top how it says plot 1, plot 2, plot 3? Those are like if you want to make scatter plots and stuff like that, which you probably did in Algebra 2 if you looked at different data and run regressions. We don't want any of those highlighted right now, so you want it to look like mine. If any of yours is highlighted, like it has the dark box around it, you need to scroll up there and press Enter on top of it so that it's not highlighted, and then scroll back down. Okay? As far as the Y1s, Y2s, Y3s, whatever, you can just go to each one and press Clear, clear out whatever is there. Okay? And we're going to go ahead and type in our equations. A couple things about the calculator. Remember, when you want to type the variable x, this button right here will do that for you. Okay? And if you want a negative, subtraction and negative are different things to the calculator. Okay? Subtraction means take something away. So if you write minus and you use this button, and then you type 3x and you go to graph it, it's going to say error because it's like, what do you want me to subtract 3x from? It's looking for something to be in front of there to do subtraction. This is the negative button. Okay? So let's go ahead and type in our 3 equations that you guys should have on your paper, and we also have it here. Okay. So 0.5x plus 1.6. 0.7. All right, so make sure that you type in the 3 equations that we have. And then if you've used the graphing calculator before, you know that there are ways where you guys can change the window exactly to what you would want. Because if you're drawing a graph by hand, depending on what the numbers are, you scale it different and you make it extend further in certain directions and stuff like that. You can do all that stuff on the calculator too. You can tell it, I want the minimum x value on the grid that I'm looking at to be this, and I want the maximum x value to be this, and I want you to make a tick mark every 1 or every 5. And you can do the same thing for y values. We're just going to look at it in a window that goes 10 positive, 10 negative on each axis. That's considered kind of the standard viewing window, so sometimes we need to change it for our purposes right now and our purposes next week. The standard viewing window will work just fine. So the quickest way, if you weren't taught or don't remember, to get to the standard viewing window is to go zoom and then to choose choice 6, which says Z standard. So you can scroll down to 6 and press enter, or you can just push 6, and then we should get our graph. Okay? So here's what we see. So question that we want to answer. Let me look back at our note guide. Does this graph represent what you saw when we graphed the data from the CBR? What's similar and what's different? So think about what you saw when we created the CBR graph. Is this graph the same? If not, what's similar about it and what's different? So what's going on here that's the same, and what's going on here that's different from what we saw after we had somebody come up here, walk, and we saw the graph that it created? So do this. Take a minute in your groups. I'm going to randomly pick a group to tell us, okay? What about this is the same as what you saw when the person was making the graph in front of the sensor? What about this is different than what we saw, okay? So take 1 minute, have that conversation, because I'm going to call on somebody to tell us what they think. Discussion. Is there someone that feels confident enough with what's going on to share out with us without being picked on? So either of you guys from this group?
It's similar in like you can see how a line can be connected to each other. But the only thing that's different is the slope keeps going. There's no like stopping point.
Good. Okay. So we know that these 3 lines existed, but when we saw it on the CBR, they didn't just exist forever, right? They only existed for certain portions of time. So like when we watched the CBR, he walked, he paused, he walked back towards it, right? And that was it. We didn't see them all intersecting and crossing each other and continuing on forever. That's because there is a mathematical notation that tells someone, I want you to graph this, which we clearly do want to graph it, but we didn't want it to start till here, and we wanted it to stop when it got here, and then we wanted to start this extra one, stop here, etc. Okay? So we want to figure out what that notation is. So we're going to come back to this page, and we're going to write our equation. So we know we need these 3 things. The question is, how do we write it properly and mathematically so that the people know about these end stopping points? Because if we just give them the 3 equation, that's what they're getting, and that's not exactly the same, right? Okay, so in order to understand the notation, though, we're going to go through a little activity where we're going to create a graph of a piecewise function so we can understand what the notation means and where they're getting the information. Those of you that have the note-taking guide, you have it on the next page. So it looks like this. Okay? All right, if you don't have it, I feel so... I can't draw a straight line, so I make a lot more points than you might have made on your graph. So check your lines and make sure you're good with what we have up there. So first line, your y-intercept's at 1, your slope is 2, so you rose 2 and ran 1. The line has a positive slope that's up there. Second line, the y-intercept's at 3.5, okay? And the slope is -1/2, so down 1 over 2, so resulting in the negative sloping line. And our third line is horizontal through 1.5 as the y-coordinate. So all these points that would have 1.5 as their y-coordinate. Okay? All right, so then let's look at what it says at the bottom and interpret what it means. So we're going to go and we're going to highlight some stuff on our graph. So on the first graph, so the graph is now what I've created, which means this line. I want to highlight the portion of my line that is in this domain. Okay? So x is less than 1. So look on the x-axis. Here is where x is 1. Okay? But I want to highlight on the graph I've created all the points where x is less than 1. So along this line that I drew here, 1 would line up with this endpoint right here, right? So everything to the left of that would be in the area where x is less than 1. Does that make sense? So I'm not going to shade the area. I'm just literally going to highlight the portion of my graph. So you can just make it darker, or if you have a different color handy, you could do that. Okay? So I'm saying with this line, if you only wanted the part that was in the domain where x is less than 1, you would be saying you only wanted this part of the line. Does that make sense to everybody? Because remember, our goal here is we don't know how to tell people like where to end something and start something. So now we know that if we just tell them to highlight or use a certain part of the domain, the x's, we can restrict what they're doing. Okay? Question about the end point right here, right at 1. Did it say it wanted you to highlight when x was exactly equal to 1? No. What is the number that's right before 1? The trick question. What about 0.8, 0.9? What about 0.99? What about 0.9999? So what is the number that's right before 1? There isn't one, right? It's like this very weird mathematical concept that you can pick any two numbers and I can find a new one in between them. There's like infinitely many numbers between any two numbers. Super weird. So remember that when you're graphing things and we want to say go right up to 1 but don't use 1, we still have to draw the point at 1, but how do we draw it so that people know they're not actually allowed to use that exact value? Yeah, the open circle, okay? So I want to go all the way up to this point on the graph, but I want it to be open at that point because I want to tell them go all the way up to 1, but don't actually include 1. And I can't technically pick out the number before 1, so I have to mark it at 1, but with the open circle. Okay? All right, so the next thing on the next graph, we want to highlight all the portion where x is greater than or equal to 1 and less than 4. So let's think about where that is. Here's 1 on the x-axis. Here's 4. So I only want stuff that's in between there, but I want the stuff that's on the thing I've already graphed. I want points on my line that are in between there. Okay, so I want this portion of the line. Okay. Now, the end point at 1. When they listed this domain, did they say x was allowed to be equal to 1? So look at x and 1. It has the equal to mark between them. So yes, so this point is a filled-in point right there. It's good. I want it covered. Okay. What about at 4 when we ended our highlighting? Did we say x was allowed to equal 4? No. We just wanted it to be less than 4. So same thing as before. I want them to go all the way up to 4, but not quite include 4. So that end point I'm going to make open. Okay. So if I want somebody to only include this part of the line, I have to tell them to only use these x's with that part of the graph. Okay? That's how I can get them to start and stop just a part of the graph instead of graphing the whole thing like we saw on the calculator. Okay? So third section, we want to graph everything that's greater than or equal to 4. So here's 4 on the x-axis. And you guys understand when I'm marking 4, this is like what's going on in my head, right? Like this mark is not part of what I'm graphing, but I'm trying to visually show you guys what I'm thinking. So here's 4. That lines up with this part of the line. I want when x is bigger than 4, so everything to the right with no limitation, so it's going to keep going forever. Now, when x was exactly equal to 4, was it allowed to exactly be equal to 4 on this graph? So I look at what x was allowed to do. It was allowed to be bigger than 4, and because of this mark here, it's also allowed to be equal to 4, right? Which means at this endpoint, I want it to be closed because it is allowed to equal that exact point. Okay. So is what we did okay with everybody? We graphed lines like we did on the calculator, like here's all the different lines. And then what we're trying to do with this highlighting is establish what is the math language that you would use to tell somebody to only use this part of it. This is the math language right here. These domain things with x between this and that. Okay? Any questions about that? Yes? Yeah, so your calculator, we're not going to go back to the calculator today and do it, but it actually has a way for you to tell it that x has to stay between certain things, and it can graph and stop exactly where you tell it. Okay? Our goal is going to be to do it by hand today. Right? So the next thing that you guys see is this. Here is the notation. Okay? So it looks super weird. This is one equation. It doesn't look like one equation, right? How many equations does it look like? 3. You know why? It's one graph, but with how many different pieces? 3 different pieces. And we want each piece to show up, but do we want it to show up the whole thing on the whole entire graph? No. So then that's why they have these weird little things listed after them about what x is allowed to be. Notice that the first piece of the function is the first line that you graphed, and that the domain restriction, the part of it that I want, you highlighted on your graph, right, when x is less than 1. So I only want the part that you highlighted of that first line. That's what I'm telling you in this equation, right? Then I'm telling you use this second piece. Notice that it's the second line that we graphed. Okay, I wanted you to already have the graphs ready. And we only want the piece of that we highlighted. That's what this means right here. Okay? Then we want this third piece, but we only want the part of that we highlighted. If you take just the highlighted parts that you have and you put them all together as one picture on a graph, you're going to have the graph of this one function with these three separate pieces starting and stopping at the appropriate places. Does that make sense to everybody? Okay? So what we're going to do right now is try to take the three things that you highlighted and draw them on this graph right here because they represent this math notation in action. Okay? And then I'm going to be working on the same thing. I don't have my picture to look at like you guys do, but oops, I think. So the first piece that you highlighted looked like this, right? Is that okay with everybody? Right? So notice I gave it a stopping point by telling someone I only wanted it while x was less than 1. Okay? Then the next piece that I wanted, sorry, 1, 2, 3 and a half, down 1 over 2. So the next piece that you highlighted looked like that, right? Now, about this endpoint right here. On the first piece, it was open. Does the second piece have the exact same point? So does the second line that you highlighted, does it also have a point at 1, 3? Yeah. And it was a closed endpoint, right? So when you have an open one, but a closed one comes and sits on top of it, how do you think people then view that? Do they view it as included, filled in, or not included and still empty? Well, in one piece it wasn't included, but then in the next piece it was. So did it get covered? Yes. So we want it to be covered. So anytime you have an overlap, as long as one of them is filled in, consider it a normal filled in point on your graph. Okay? So I'm not going to leave that open. It would just appear like any other normal point because the second piece overlapped with it. If the second piece didn't happen to start at that exact same spot, say it started up higher or down lower, I would have had to leave that endpoint open from that first graph because it wouldn't have been overlapped by something else. Okay? And then our third section looks like this. Okay? So this graph with these three different pieces is the graph of this function, and here's how we write it, right? One more time. We write the equation of each piece on its own, so we have to know how to write equations of lines and graph lines. We then also have to put these things next to them to tell people where to start and where to stop. Okay? All right. Now, a couple of things. Is this a function? You guys remember like your vertical line tests, algebra 1, algebra 2, okay? Does it pass the vertical line test? Yeah, okay. It's a weird looking function, right? It's not what we would normally think of as a function, but yes, this is a function. Okay? And then you'll hear this word in your math career also. Is it continuous? This actually means exactly what you think it means in English. Like, can you draw the graph without picking up your pencil? Like, could you start over here, trace this whole thing without ever picking up your pencil? Yes, then you're continuous because you didn't have to lift up your pencil, all right? If some of these endpoints where we went from one type of equation to another were not overlapping and connected, then we might have something that is discontinuous or not continuous where we have to start at a new spot, okay? All right, domain and range. So remember like Jay-Z and Spider-Man, right? Okay, so domain across the graph. Okay, as you move from left to right, is there any place where the graph ends or has a hole, any x values that are not included? Okay. So look, it goes forever this way. So if I keep picking x's over here, will I find a spot that corresponds on the graph? Yes. Okay. As I move here, if I keep picking x's somewhere out here, will I find a spot on the graph that corresponds to them? Yes. There was no x's skipped. Okay. There was nothing I couldn't reach, so the domain would be all real numbers. All right, range. So shift to look at it vertically, up and down. Okay? Are there any gaps vertically where you don't reach certain y values? Or is there anything that you reach and you can't go any higher or something you reach and you can't go any lower? Those are kind of the things that you're looking for. So are there any restrictions? Can we go forever downward? Can we get every y? Yeah, sure. You want a y way down here? Sure, there's something on the graph over here that meets it. Okay. What about upward? Can you go forever upward? No. You kind of hit a maximum that is the maximum you will reach on this graph, which is what y value? 3. Okay. Do we actually hit 3? Yeah, because it's a filled-in point at 3, right? So we can be 3 and anything below it, but that's it. So we say that as y can be less than or equal to 3. All right, so tomorrow when you get your homework, and we're going to start it in class and do one together and this kind of thing, and you might be able to finish it in class, just depending. You're going to get problems that look like this right here, okay? And you're going to be asked to graph them. So you now know what that means. You want to graph this line, but only in this area of the graph. You want to graph this line, but only in this area of the graph. And this one, but only in this area of the graph. Does that make sense to everybody? Okay, so you're not learning a new graph. You already know how to graph the lines. It's just about putting them in the right place, okay? So we'll practice that a little bit, but we should be able to read it and understand what that equation is asking us to do, okay? All right, the last thing I want to do is I want to go back to this then and decide how do we write the equation that we created yesterday on the CBR. We tried it. We got equations. We put them in the calculator. We had the right shape, but we didn't cut things off at the right spots, okay? So we need to go and do that now. So go back to your notes on the CBR, and we're going to create an equation. Okay? So first of all, remember what ours generally looked like. I know this isn't perfect, but he walked away, he stayed still, and he walked back towards. Okay? How many pieces would we expect our piecewise function to consist of to represent this graph? 3. Okay? So I'm going to make that weird little bracket thing because I know I've got to have room to write 3 different pieces of it. Okay? We already wrote the 3 equations, so we already have the pieces that we need right here. Piece number 1, piece number 2, piece number 3, right? We already figured that out. We did all the work for writing equations of lines. So I'm going to go ahead and write those down. Piece number 1 was 0.5x plus 1.6. Piece number 2 was just y equals 2.7. Notice I don't write the y equals every time. The f of x is like the y equals, okay, and it's being used for each piece. And the third piece was negative 0.6x plus 4.19. This is basically what you guys put into the calculator. What we didn't put into the calculator was this information about where each thing was taking place, and we now know those need to be included in the equation if we want to tell someone to only use a certain part of it, okay? So this first line right here, think about the x-axis. Okay. When did it start? Does it go forever to the left, or did it start at a specific time? It didn't start at 1.6. That was the y-intercept. That was the distance, but time-wise, 0, right? We couldn't go to negative time, so we started at time 0, okay? So 0 was where it started, so I know that x values can be bigger than or equal to 0. Okay? And it didn't go on forever, so I need to also say that x then has to be smaller than something. So the question is, time ticked. Where did we reach that time ticking mark where all of a sudden we cut the graph off there and we started something here? Okay? So we made a note of it, right? This section seemed to end when we hit 2.6 seconds, right? So I want to say that here. I want to say you can't use this graph past 2.6, okay? So I would tell them stop at 2.6. Now, when you're writing your own equation, if you want to, you could put an equals to here and then not include it in the next one, or you could leave this one empty and include it in the next one, because who really knows, was it this endpoint or this endpoint that ended up making that closed on the graph? We don't know, so it would be right either way. Okay? All right, so then we get to the second section of the graph. So we now know at 2.6 we stopped that and we started this motion. So in this motion, x has to be greater than or equal to 2.6. We cannot start this second portion until 2.6 and later. And then that portion is going to keep going while time is ticking until we reach some amount of time where all of a sudden he decided to move and do something different, right? So what was this time that we reached where we have to stop this type of action or this line? Yeah, 3.5, okay? So this continues until 3.5 seconds. So I can only use this equation. He only stood still while time was ticking from 2.6 to 3.5 seconds from when we started, okay? Then he started moving again, so I have to follow this pattern or this equation. Okay? That started at 3.5. So I want x to be more than 3.5 because I want it to go after 3.5. Okay? Until the end. Now, you could argue like this is good, it just goes on forever. But we didn't keep moving forever, right? Eventually the time stopped ticking and stopped collecting data. So this ended for us at 5 seconds because that's how long it went and collected the data for or whatever. Okay? So this is going to stop at 5, and it did actually have a point at 5 that said at 5 seconds he was at this position. So I'm going to include 5 and say it counted all the way up until that 5th second and included it. So what is this going to help us with? There's going to be a second section on your homework tomorrow. So first section is going to be they give you the equation, you make the graphs of it, right? So you sketch each line in the right area and connect it the right way. Or it might be disconnected, right? Second section is going to have some graphs, and your job is going to be to write the equations of each section and put the correct domains next to them for when one started and the next one, and the next one, etc. Does that make sense to everybody? Okay. So 2 ways. If someone gives you the equation, can you graph it? If they give you the graph, could you produce an equation? We've technically done both of those things today. Okay? And honestly, if it's where you're trying to make the graph, worst comes to worst, you do exactly what we did in the notes. Take each piece and graph it separately, right? And then erase the piece you don't want or highlight the piece you do want and then put together your final graph. Does that make sense to everybody? It takes a little bit longer, but if I'm going to let you take the extra time, if it's going to be the difference between getting the problem right on the test or getting the problem wrong, being able to graph a piecewise function versus not being able to, might as well take the extra time and figure it out, right? And we'll talk about other ways we can do it that might be a little shorter, but if worse comes to worse and you understood how to do that today, and then just take the 3 pictures and put them together on one, then do that every time. Does that make sense to everybody? Okay, that's why we did it that way. So you have, like, if all else fails, I can do it like this. Okay? All right, so that's it for today.